Hello, are you able to hear me?
Yes, sir.
Oh, good. Right. Today I would like to discuss about concurrent hashing. Before going to discuss about concurrent hashing, I would like to give the brief introduction on hashing. Okay. I think you heard the term hashing, right? May I know the applications of the word hashing? May I know the applications of hashing, where this hashing technique is used?
A key exchange and CRC checking.
Yeah, that's
Um,
that that's good. Yeah, hashing is used in cryptography and network security. Other than that, other than that. Usually we can use the hash tables, right? For what purpose we are going to use the hash tables? Hash table is a kind of data structure. Okay, we can store the data in that particular hash table and we can perform the operations on that. Usually what are the operations we can perform on the hash table? Simple insert, delete, and search operations. Are you with me?
yes, sir.
Okay, right. When we look at this particular hash table, okay, usually how much amount of time is it going to take to perform insert, delete, and search operations? May I know the time complexity of um, time complexity of basic operation on a hash table? Okay, good. May I know the time complexity of basic operations on the hash table? We can perform all basic operations uh, in order of one. Amortized time. Okay, amortized time means average over P operations. That is the time complexity of hashing. That means uh, that particular hash table more or less supports so much amount of parallelism is there in that. So suppose, is it possible to parallelize the hash table? So before going to proceed further, here I would like to give a simple idea on that particular one. This is a simple hash table, right? What is the size of this hash table? Here, size. What is the size of this hash table? When we look at that particular hash table, size is 4, right?
Four.
Okay. Suppose if you want to perform some operations on that particular hash table, what are we going to do? Suppose if you want to insert a particular key into that particular hash table, we make use of this hash function. Okay, here I considered a very simple hash function, h of k equal to k mod 4. That is a simple hash function. With the help of this particular hash function, when we insert these two keys, okay, those two keys are inserted into the appropriate buckets. Here we have four buckets, okay. In bucket 0, we have only one element. Bucket 1, we have only one element. Bucket 2 and bucket 3 are empty. Right. Now, suppose if we insert 7, 7 is going to be inserted in bucket 3. Okay. Why? Reason is 7 mod 4, remainder is 3. If remainder is 3, that particular value is going to be inserted into that particular bucket. Suppose if you consider that particular add operation, okay, what is the time complexity of add operation? What is the time complexity of add operation here? Any guess?
Order of one.
That's good. Order of 1. Here we are performing simple hash function. We can calculate that particular hash value in 1 unit of time. After that, we are going to perform insert operation in 1 unit of time. So 1 plus 1, it is 2 units. 2 units is become, it is order of 1. So next one is, suppose if you want to insert one more value. Suppose if 4 is inserted, Okay. Then 4 is inserted into the bucket 0. Yeah, here, when we look at this particular one, there is a collision. Okay. In a hashing technique, what is the meaning? What is the definition of the word collision? Any guess? If two or more keys hash to the same bucket, then we can say that that is a collision. Are you with me? Suppose if we consider this simple example, here we have two keys, 16 and 4. 16 mod 4 is 0 and 4 mod 4 is 0. Both the keys are hashing to the same bucket, then we can say that there is a collision. If there is a collision, in that context where the new key is going to be added, the tail end or at the front end, okay? That is based on our choice. Okay? If you want to add it at the front end, you can add it. Or if you want to add it at the tail end, we can add it. It's not a big deal. Next one. Here also there is a collision. Actually, we can insert it. Suppose if it has hash table size is fixed, we keep on increasing the number of keys. Then what will happen if for a fixed hash table size, we keep on adding the keys? Then what is going to happen? What is going to be happen?
Collisions.
Yeah, more collisions. If we have more collisions, then what is the problem? Yes, what you said is correct. Actually, collisions. If we keep on adding, then we will get the collisions. But when we look at the definition of the word hash table, okay, hash table is a data structure that supports uh, basic operations. That means insert, delete, and search operations in a constant amortized time.
It can degrade the performance.
Yeah. Actually, that condition is going to be violated.
Okay.
Suppose take in this particular one, suppose if we insert n elements or if we add n elements, okay, then the average length of the each bucket is approximately n by 4. If average length is around n by 4, then its time complexity to perform insert or delete, okay, is n by 4, right? Are you with me? Not only that particular insert operation, suppose if you want to perform a search operation, in that context, search operation time complexity is order of n by 4, right? Order of n by 4 is order of n. Okay. So in that context, what is the difference between hash table and linked list? We don't find any difference. Suppose to reduce the search time, what can be done? To reduce the search time, what can be done? Any guess? To reduce the search time, here problem is buckets becoming too long. Here our objective is we have to reduce the bucket length. To reduce the bucket length, what we have to do? How can we reduce the bucket length? Any clue? If we change the table size, here table size is 4. If we increase the table size to 8, then what will happen? The average length of the bucket is going to be changed, right? Did you get my point? Here, what is the average length of the bucket? Here,
Force.
yeah, here average length of the bucket, here it is 2, here it is 1, here it is 2, 5 by 4. Here average, for in this case, 5 by 4. Okay. Suppose if we double the table size, in that context, table size double means instead of 4, we are going to consider 8. Okay. Then average length of the bucket is 5 by 8. 5 by 8 is less than 1. Or we can say that it is approximately equal to 1. So in that context, we can reduce the search time, right? If we double the table size, we can reduce the search time. Did you get my point? Okay, right. Uh, I would like to give a very simple example. consider few more keys. Suppose we are going to add node 20 and node 40. Node 40. We are going to add node 5, node 13, node 21. Okay. Suppose for this particular problem, what is the average length? The average length of this particular one is here. We are going to consider length of this particular chain. Length of this particular chain is 4. Next one is also 4. Here it is empty. Next one is 2. That is 10 by 4. Okay. Average length of the bucket is uh, 10 by total number of buckets. That is 10 by 10 over 4. That equal to 2.5. So we have to perform on average to such an element in this particular hash table. On average, we have to perform 2.5 comparisons. Okay. Suppose if we double the table size, instead of this 4, if we double it, then what is the average length? Average length of the bucket is 10 by 8. It is close to, it is 1.25. 1.25. That means we can search a node within 1.25 comparisons. That means we can reduce the time. We can reduce the time. So why do we need, why are we giving so much importance to this search operations? Here, point is, here we are giving so much importance to the search operations. What may be the reason?
To reduce the catch miss.
Yeah, to not only to reduce the cache miss. Here, when we look at the real-time workloads are usually 90% of the operations are contains operations. When we look at the real-time workloads, 90% of the operations are contains operations, 9% operations are insert operations, and only 1% is delete operations. Only 1% is delete operations. This is the real-time workload. So if most of the operations are contains operations, okay, if we use data structures that gives the very less time, less such time when we perform this many number of comparisons, when we perform that many number of contains operations, then we can reduce the execution time or we can reduce the search time, right? Is it clear? Suppose here consider simple case. Okay, if search time is 1 unit, actually in a hash table, search time is more or less close to 1 unit. So in this context, 90% of the contains operations can be performed in 90 units of time. Insert operations. Suppose in the hash tables, when we perform the insert operations, most of the times there is no need to resize the hash tables. If there is no need to resize the hash table, we can perform the insert operation in 1 unit of time. Sometimes we have to resize the hash table. In that context, such time is order of n. Okay, yes, where n is the number of elements in that particular hash table. Actually, deletion, usually for deletion operations, we don't resize the hash table. Sometimes there is a need to resize. Okay, in that context, a time complexity is order of n. That is very worst case scenario. Okay, with that idea, I would like to discuss this particular hashing technique. Okay, right. When you look at this particular one here, buckets are becoming too long. When buckets are becoming too long, what we have to do? we are going to resize the hash table. We are going to increase the size of the hash table. Instead of 4, here we are going to consider hash table of size 8. So whenever we consider hash table of size 8, then we are going to change the hash function. Instead of considering k mod 4, we are going to consider k mod 8. Okay, whenever we consider k mod 8, we have to rehash all the existing keys. That rehash all these existing keys. Okay. So in that context, when we rehash all the existing keys, okay, what do we get it? We observe that, okay, again we have to rehash 4 with the help of new hash function, that is 4 mod 8. That is 4 is going to be added to the new bucket. That is 16, there is no change. And 9, there is no change. Again, which element is going to be changed? 15 is going to be changed. Whenever we perform 15 mod 8, that is 7, that one is going to be added. Okay. What is the problem? Yeah, 15 is going to be added and 7 is going to be added here. Are you with me? Are you with me?
Yes, sir.
Yeah. This is the simple operations on a hash table. Okay. So this is simple insertion. You know how to perform the such operations. Suppose to perform a such operation in a hash table, suppose if you want to search X, what we have to do? We have to calculate X mod 8, X mod 8, then we'll get the appropriate bucket. Bucket is some M, then its value is some M. Then we go to that particular bucket, okay, and perform the search operation in that particular list. And perform the search operation in that particular list. In the particular list. Next one is uh, delete operation. Okay. Yes. To perform a delete operation also, we have to identify the appropriate bucket. After that, we will get a simple linked list. Okay. Do you know how to perform delete operation on the linked list? Okay. Are you with me? Now you have some idea on how to perform insert, that is add, search and delete operations. Is there any difficulty while understanding this particular one? Because I'm going to explain concurrent insertions, concurrent deletion, and concurrent search operations. That is why initially I covered simple insert, delete, and search operation. Is there any problem while understanding this? If there is no problem, I will move to the next slide. Can I move to the next slide?
Yes, sir.
Okay, right. Yeah, next one. Suppose if we want to perform operations on this particular hash table, how can we perform concurrent operations on this particular hash table? How can we perform? Any guess? Any guess? You studied different types of you actually I delivered lecture on different types of synchronization, right? Coarse grain synchronization, fine grain synchronization, okay, lazy synchronization, different types of synchronization techniques are there, right? Suppose if there is a need to implement concurrent hashing, then what can we do? Okay, we can develop a simple coarse grain uh, hashing technique, right? Suppose if you want to develop a coarse grain hashing technique, what can we do? What can we do? Coarse grain means we are going to acquire the lock on large chunks of the data. So in that context, for this entire table, this is a table, right? For this entire table, we can keep one lock. We can keep one lock. Yes, threads. Suppose if we are working with the threads T1 and T2, thread T1 acquired this lock. Then we are going to allow thread T1 to perform the operations on this. T2 is going to spinning on that particular one itself, right? After some time, T1 is going to release the lock. When T1 releases the lock, T2 acquires the lock and perform the operations on that particular one. That is a simple coarse grain locking mechanism, right? We can implement this concurrent hashing by using that particular simple coarse grain locking mechanism. Is it possible? Is it possible? In coarse grain synchronization, we can acquire the lock on large chunks of the data. Here we are going to acquire the lock on data structure level. Here, what is the data structure? Hash table is the data structure, right? We are going to acquire the lock on the hash table. We are going to perform operations on the particular hash table. What are the operations we can perform? We can perform insert, delete, and search operations on that particular one. That is one way of implementing concurrent hashing. What is the problem with that? What is the problem with that? Did you find any problem with that particular concurrent hashing? When we are working with multiple threads, those multiple threads creates a contention at the root node or at the data structure level. Okay, if these multiple threads creates contention at the data structure level, then what will happen? Actually, performance is going to be degraded. Are you with me? Are you with me?
Yes, sir. So the
Yeah,
thread 2 will be waiting for until the thread 1 releases the lock.
yeah, that is the case. Now, I would like to show the results. Why performance is going to be degraded. Okay, uh, because I informed all of you ahead of time, right? Okay, I don't want to concentrate on theory. I would like to demonstrate all these things by writing a simple program. Okay, I would like to show the results. I think you are able to see the screen, right? Are you able to see the screen?
Yes, sir.
Okay. VI course hash set. This is the course grain implementation of hash table. When you look at this particular course grain implementation of hash table, here what can you see? Okay, here you can see that this is the class hash set extends base hash set. Okay, what is the meaning of the word extends? Very simple feature of Java and C++, right? Base hash set is the base class, and course hash set is the derived class. Here in derived class, we are using the methods and functions which are defined in the base hash set, right? Are you with me?
Yes, sir.
Okay.
Inheriting.
Yeah. So for better understanding, actually, we here what we have to do. Okay, we should have some idea about what are the methods or which methods are available in base asset class. For that, initially I would like to discuss base asset. BI base asset. When we look at this particular one base asset, what can you see? You can see that few methods are there, right? Okay. In any job, in any one, we think about this is the construct of the class, base class. Okay, when you look at this particular simple constructor here, what can you observe? You can observe that we are allocating the some amount of memory to the hash table. This is the table. Okay, we are creating a table here with the help of this particular statement. Once table is created, so table is some that is a kind of set of buckets, right? Okay. Suppose when we create a table, the four buckets. This is one bucket. This is another bucket. This is another bucket. Here in this bucket, we are going to store some set of elements, and here also, we are going to store some set of elements. Okay. To store those set of elements, we are using the array list. We are using array list. So with the help of those two statements, okay, we are going to create a hash table. Hash table is some set of buckets. Each bucket, we are creating each bucket with the help of array list. Are you with me? Is there any doubt while understanding that particular constructor? Do you have any doubt? Can I proceed further? I need a little bit response from you. Can I?
Yes, sir. Yeah, yeah, yes.
Yeah, right. Now we created a hash table. After that, what are the operations we can perform on the hash table? Contains operation, and the next one is add operation, next one delete operation. Suppose if you want to perform a contains operation, what we have to do? Suppose if you want to verify whether X is there in that list or not, what we have to do? We have to perform that mod operation, right? Where is the mod operation? That is, we with the help of X dot hash code, we'll get that hash code for a given key. Okay, mod table length. With the help of that, we can identify the appropriate bucket. With the help of this, we can identify the appropriate bucket. Once we identify that particular bucket, okay, we can go to that particular bucket, table of my bucket dot contains. That means we are going to call this method of array list. We can simply verify that whether the given key is there in the particular array list or not. Instead of array list, we discussed about different linked lists, right? You can consider that particular linked list also. It is not a big deal. Okay, this is simple one. Suppose when I look at this particular one, okay, these are the set of statements we are going to perform in a contains operation. Okay, before going to perform these statements, okay, here we call one method. And we'll what is this method? Acquire of X. That means we are going to acquire the lock. Okay, after acquiring the lock, okay, we are going to execute some set of statements in a try block. After that, once we come out from the try block, it is going to call statements which are there in the finally block. Finally block, what is there? Release of X. Okay. So here in that particular contains method, before going to perform those two statements, okay, that is which statements which are there in try block, we are going to acquire the lock with the help of acquire of X. Next, after that, we are releasing the lock. Whenever we call acquire of X, what is going to be happen? Any guess? We are going to acquire the lock on the entire data structure. Where is the method for that? Where is the method for that? Definitely not. Acquire of X is not here, right? Is it here? When you look at this particular piece of code, here contains is there. Similarly, it is add method is there, remove method is there, and print table is there. Do we have acquire method logic for acquire of X?
No, sir.
No. Here we declared that particular one as abstract method. If it is declared as an abstract method, we can give the definition for that one in the derived class. We can give the definition for the word in derived class. Okay. Just like that, you can understand the methods which are there in, you can understand other methods of this particular base asset. Here, I would like to discuss the method which is add method. Anyhow, I will share the code. You can easily understand the code of remove method. When we look at this particular one, add method. Okay, when we look at this particular add method, what is the return type of this add method is Boolean. That means on successful insertion or successful add operation, this particular method returns true. Otherwise, it returns false. Initially, we are assuming that result is false. Okay. After that, here we are acquiring the lock. That means we are going to perform these statements in the add method. So before going to execute these statements in the add method, we are going to acquire the lock on a lock on X. Once we acquire the lock on X for a given key, given X, okay, we are going to identify the bucket, okay, on which bucket we have to perform the insert operation. We have to, similar to the previous one, we are going to identify the bucket. After that, we are going to call table of my bucket dot add. That means this is simply add method in linked list. Okay. When we perform the successful insertion, linked list add method returns true. Otherwise, it returns false. Okay. If if it is true, then we are increasing the size. This is size is a variable that is used to maintain number of items there in that particular hash table. Why do we need to maintain the number of items in the hash table? Sometimes there is a need to call resize the hash table. Sometimes there is a need to resize the hash table. So for that reason, we are maintaining that particular size information in that variable size. After executing these three statements, we are releasing the lock. We are releasing the lock. Okay. Next, that is simple add method. Here in this particular add method, we called one more method, one more thing. We performed one more operation. What is that operation? That operation is resize, right? When do we call resize operation? We are going to consider some policy. Okay, what is that policy? Policy is if average length of the bucket is greater than so and so, then we are going to call resize method. Okay. Why? If average length of the bucket is greater than so and so, what will happen is it increases the average search time. If average search time increases, there is no need to consider hash string technique. We can consider some other technique. Okay. Here, what are you going to achieve in hashing technique? We are going to achieve the average search time is constant, order of one. Then only we consider this particular hash table data structure. Are you with me? Are you with me?
Yes, sir.
Okay. Here, when we look at this particular one, similarly, you can understand the remove method. Nothing great in that. Okay. That is simple base hash set class. In base hash set class, we are creating a hash table with so and so size. After that, we are going to call contains method, add method, and remove method. Here, we haven't declared the logic for acquire X and release X. Okay. Next one. We are calling this particular base hash set from the course hash set. When you look at this particular course hash set class, here what can you see? Here you can see that few more methods are there. Okay. Here, suppose if you want to create an hash table, what will happen is so and so capacity. We want to create an hash table with so and so capacity. Here we are calling super of capacity. That means with the help of this particular one, we are creating a base hash table. We are creating a hash table with so and so capacity. After that, here you look when you look at the one more statement is there here. What is that? That is lock is a variable. This lock variable holds an object of type reentrant lock. That means with the help of that particular lock variable, we can acquire the lock on entire object. With the help of that particular lock variable, we can acquire a lock on the entire object. Are you with me?
Yes, sir.
Are okay? Are you with me? Right. Right. Here, when we look at this particular one, you can observe that here you can observe that here in this particular one, you can see two methods, right? This is one method that is acquire of X. Acquire of X, we are going to call lock. Lock dot lock. Here lock dot lock is there in acquire X. Here lock dot unlock is there in release of X. What is the meaning of that? Okay. Whenever a thread calls acquire of X, it is going to acquire the lock on the entire data structure. Whenever a thread calls release of X, it is going to release the lock from the entire data structure. Is it clear? Is it clear?
Yes, sir.
Yeah. So whenever we look at that particular base asset class, in this base asset class, suppose if you want to perform any basic operation, either contains, add or delete operations, before going to perform any basic operation, there we are going to call acquire of X. Okay. That means we are going to acquire the lock on the entire data structure. After that, we are going to execute some set of statements. Later, at the end, we are going to release we are going to call release of X. When a thread calls the release of X, we are going to release the lock from the entire data structure. Okay, this is simple hash table. Okay, are you with me? Are you with me?
Yes, sir.
Yeah. Now we are going to test performance of this particular hash table. Whenever we look at the performance of this particular one, yeah, I wrote a wrapper class for that. In that particular wrapper class, I consider this particular object of type course asset. Here we are working on this particular one. Java C has test.java. There is no problem. Okay. Java has test. First argument is the number of threads. Second argument is the size of the range of the keys. And third argument is time. And fourth argument is of percentage of prefill. If range of keys is 20,000, we are going to prefill that particular data structure with 50% of the elements, that is 10,000 elements. Next, insert is 50%. Difference between 75 and 50, that 25 is insert operations, that is 50% contains, 25% insert, remaining 25% delete operations. When the number of threads is 1, we can get at least 1.15, that is the throughput. Okay, that is throughput is 1.15. Here we are going to increase the number of threads. When we increase the number of threads, what can you see? You can see that throughput is 0.7. Throughput decreases, right? Suppose as we increase the number of threads, we're supposed to get the better throughput. But here throughput it decreases. What may be the reason? This is because of
Entire lock.
a entire lock. This is because of core strain synchronization. Okay, to increase the throughput, what we have to do, instead of core strain synchronization, we have to build a logic for fine grained synchronization. We have to build a logic for fine grained synchronization. How can we build a logic for fine grained synchronization? Instead of acquiring the law on entire data structure, what can be done?
So only for inserting and deleting we can acquire the lock. For content search we don't want to.
Yeah, that is good suggestion. Next one is that is good alter. Next one is this is one linked list, right? This is another linked list. This is another linked list. All these linked lists are independent of each other, right? So if one thread wants to perform operations on this particular one, if second thread wants to perform operations on this particular one, if third thread wants to perform operations on this one, fourth thread operations on this one, all these threads can perform the operations on those four linked lists simultaneously or at the same point of time. Is it possible? Is it possible? Yes, it is possible. When it is possible, when it is possible, if we maintain separate lock for each list, then it is possible, right?
Yes, sir.
If we maintain separate lock for each list, then we can perform all these operations in one go or at the same point of time. Okay. For that, what we have to do? We have to acquire a lock on all all the buckets, right? To acquire the lock on all the buckets, this is the case, right? Suppose if you consider the simple example, here we are going to acquire the lock on all the buckets. Are you with me? If we acquire the lock on all those, suppose no, not all those buckets. Actually, here we are going to maintain one more table, that is lock table. Okay, that lock table. This lock is responsible for this particular bucket, that is bucket 0. This lock is responsible to perform operations on bucket 1. This lock is responsible to perform operations on bucket 2. This lock is responsible to perform operations on bucket 3. Is it clear? Is it clear?
Yes, sir.
Yeah, that is clear. Okay, so what kind of synchronization here? This is a fine grain synchronization. Previous one is a coarse grain synchronization. This is a fine grain synchronization. Okay, right. Next, do you have any problem with this particular one? Do you have any problem with this particular one?
Many locks are there, and if we extend the hash table, then locks also will extend.
Yeah, when we extend the lock, actually, suppose if you keep on adding the keys, what will happen is we have to resize the hash table. We have to resize the hash table. Okay, the resizing the hash table is somewhat easy. Okay, suppose if one thread is responsible to resize the hash table, then what you have to do, that particular thread is responsible to acquire the lock on all these buckets. That for suppose T1 is going to resize the hash table. In that context, T1 should acquire the lock on all these buckets, and that particular thread will be allowed to perform the resize operation. If we allow that particular resize operation, what it does, it is going to resize the table. Okay, once it is resized, allocate the new super table and perform the operations on that particular one. Okay, now actually that particular thread is going to create a new table. And once it creates a new table, we are going to take the old all the table entries from the old hash table, and we are going to rehash it into the new hash table. Once we rehash it into the new hash table, what we have to do? Yeah, this is very simple and straightforward. We have to rehash into the new hash table. After that, we can neglect that old hash table. That means we can neglect the hash table with green color, right? So we can neglect this particular one. We are going to consider this particular pink one. After that, what we have to do?
You have to resize the lock tables.
Yeah, resizing the lock table. Actually, that is a good approach, but that is somewhat little bit difficult. Okay, before going to that resizing the hash table, what can be done is we can give this particular table to control this particular new table, right? We are going to use the same lock table to control that new hash table. Okay, in that context, each lock is responsible for how many buckets?
2 buckets.
2 buckets. In that context, each lock is responsible for 2 buckets. Okay, C. So in this context, what with this particular lock is responsible for this bucket. At the same time, this lock is responsible for this bucket also. This lock is responsible for this bucket. At the same time, this lock is also responsible for this bucket. Similarly, this lock is responsible for this bucket, last one. This same lock is responsible for this bucket also. Okay. Here, when we look at this particular simple approach, here we are resizing the hash table, but we are not resizing the lock table. When we resize the hash table and when we don't resize the lock table, again, as the table size keeps on increasing, again, there is a problem of coarse grain synchronization, right? Again, one lock is responsible for many buckets. Again, here their problem is one lock is responsible for many buckets. How can we overcome that particular problem? We can overcome that particular problem, okay, uh, by increasing the lock table size, okay. Okay, suppose as we increase the hash table size, during the same time, we can increase the log table size, then we can address that particular problem. Are you with me? Are you with me?
Yes.
That is little bit tricky one. Okay. First, I would like to execute the results of, I would like to execute the results of fine hash table. In the fine hash table, we are not going to resize the log table. We are going to resize the hash table whenever there is a need. Based on that, we are going to perform the operations on that. Okay. When we look at this particular one, VI, fine hash table. Okay. Yeah. That is, I can say that that one is stripped hash set. That is stripped hash set. When we look at this particular stripped hash set mechanism, here, when we look at this particular one, when we call this particular stripped hash set, here super of capacity means we are going to call hash table. After that, here we are going to maintain a log table. This is the log table's code for to create a log table. When we look at this particular one, uh, here what can you see that we are suppose if we create a table hash table with length 10, okay, then we are creating a log table and then length of the log table is also 10, okay. Suppose as we keep on increasing, we are we are resizing this particular hash table to 20. After that, we are resizing the hash table to 40. After that, we are resizing the hash table to 80. In that context, we are not going to resize the log table. Okay, when we don't resize the log table, so in that context, each lock is responsible for 8 buckets. Each lock is responsible for 8 buckets. Okay, in that context, up to some extent, we'll get the speed up. Beyond certain limit, here this particular implementation also faces some problem. Okay, to overcome that particular problem, what can be done? To overcome that particular problem, we can resize this particular log table also. Suppose whenever we resize the hash table, at the same time, we can resize the log table to 20. After that, whenever we change the hash table from 20 to 40, during that time, we can resize the log table to 40. Whenever we resize the log table 40 to 80, during the time, we can resize the log table to 40 to 80. In that context, we can get the better speed up. Okay. Now, when we look at this particular add method here, you know, what is the add method? Add method is going to call. Where is the add method? Add method is in the base asset. Whenever we call this particular add method of base asset, it is going to call acquire of X. So what may be the logic of acquire of X in this particular stripped asset implementation? when we look at this particular acquire of x, what is going to be happen here when we look at this particular one? Suppose if you want to acquire the log, okay, or if you want to perform an operation, add of x, okay. Here operation is, suppose operation is add of x. This is the operation. So while performing this particular operation, okay, we are calling the method acquire of x. Whenever we call a method acquire of x, what will happen is it acquires the log. How it acquires the log? For a given key or for given x, we are going to calculate hash code, this one, a bucket value. That means my bucket of for the given key. Once we calculate the my bucket, after that, with the help of this statement, logs of my bucket dot log. That means we are going to lock only that particular bucket. We are not going to lock the entire data structure. Okay. Once we acquire the lock on that particular bucket, we are going to perform some set of operations to perform the required add operation. After that, we are going to call the release of the lock. To perform the release of the lock, again we are executing the same statement here. With the help of that, we can get the my bucket value. After that, we are going to, that particular thread releases the log from that particular bucket with the help of logs of my bucket dot unlock. With the help of that, we can release the log. Are you with me? Are you with me? Is there any
Yes, sir.
doubt? Okay. Now, I'm going to execute this particular piece of code. See that wrapper class is has test.java. Okay. Instead of course has set, we are going to consider stripped has set. Okay. Java C has test.java. We compiled it. Next, after that, we are going to execute it. And the number of threads is 1. Yeah, it is 1.15. More or less, it is same. And the number of threads is 2. And the number of threads is 2. In the previous case, throughput reduces, right? From 1.15 to 0. Here, 1.71. That means actually here we are getting the better throughput, right? Are you with me?
Yes, sir. Yes,
Earlier,
sir.
it reduces. Now it increases from 1.15 to 1.17. Here, what is the speed up is close to 1.5x. Next one, instead of one thread, two threads, if we execute with four threads, let us see. Here, again, it increases, right? Instead of from 1.17 to 2.29. When we use the coastline implementation, throughput reduces as we increase the number of threads. When we consider the stripped asset implementation, throughput increases as we increase the number of threads. Okay, but this is up to certain limit. As we keep on increasing the number of threads to certain limit, again here also we face the same problem. To overcome that particular problem, what can be done? To overcome that particular problem, we have to consider some other technique. What is that technique? Instead of stripped hash set, we have to consider refinable hash set. In refinable hash set, what can be done? We can resize the entire log table. Okay, along with the hash table, we can resize the hash table. When we resize the hash log table, okay, we will get the better speed up as we increase the number of threads. Here clearly see, whenever I change that particular one, here C name is a class name. This is stripped hash set. Compile it, no problem. See, I would like to execute it for 4 threads. It is 2.87. Did you see that? Did you see the improvement here? Here, when I consider stripped hash set, when the number of threads is 4, throughput is 2.29, right? Here, when the number of threads is 4, whenever we consider refinable hash set, throughput is 2.87. Here we can increase the throughput, right? Reason behind that is, okay, in refinable hash set, whenever we resize the hash table, along with that, we are going to resize the log table. Okay. So that is about hashing technique. Okay. Right. Anyhow, what can I do is I'm going to share all the slides. Okay. Actually, here I explained only part of it. I'm going to share all those slides with you. Okay. And these programs with you. Go through the slides and execute these programs. Okay. Do you have any doubts on this particular hashing? I will clarify all your doubts in the next class because you have sufficient time, right? You have 3 to 4 days time. Meanwhile, what you can go through all the slides. Do you have any problem? Okay. And execute these programs. If you are unable to understand these programs, okay, I will clarify your doubts in the next class. Okay. In the next session, I would like to discuss skip list. You have some idea about skip list. I would like to discuss concurrent implementation of skip list. Is it okay? Or can I focus on this stripped asset and refinable asset? Choice is yours. If you ask me to teach skip list, I can teach skip list. Or otherwise, if you ask me to concentrate on stripped asset and refinable asset, I will explain the code. I will discuss how that particular resizing is done and all those things. What is your choice?
We can go for the new topics.
Okay, right, right, good. Thank you. Please come back by 7:15. Okay,
Okay.
thank you. Hi, are you able to hear me? Hello, are you able to hear me?
Yes, sir.
Yes, sir.
Right, thank you. Huh. In this session, I would like to discuss concurrent implementation of skip lists. Okay. Actually, in the beginning, we discussed about lists, right? Yeah, while discussing about list, okay, we discussed about order list. Okay. When we look at the definition of the word order list, in an order list means all the elements in that particular list are in sorted order. That is an order list. Okay. Next one, when we look at the skip list, what may be the definition of the word skip list? What may be the definition of the word skip list? Actually, in the name itself, if we want, actually, we can skip some number of the elements, right? Skip list means that, okay, there is a list that allows to skip some number of elements. Okay, those lists are called skip list. Okay, right. Okay, why do we need skip list? Okay, usually in simple linked list, if you want to perform insert and delete operations. Usually to insert and delete, time complexity of insert, delete operation depends upon length of the list. If the length of the list is n, what may be the time complexity to perform any basic operation? May I know the answer for that? If the length of the list is N, may I know the time complexity to perform any basic operation on that particular list? Is it is order of
Order of n.
order of n. That depends upon length of the list. Okay. Suppose when we skip the some number of elements in the particular search process, okay, then we can reduce that particular time complexity. Instead of order of n, we can perform any basic operation. Okay, either search, insert, delete operations. Okay, any basic operation can be performed in order of log and time in expected case. That means in an average, okay, we can perform order of log and time. Okay, this is a simple probabilistic data structure. Okay, we are going to build this particular data structure with based on some probability. Okay, yes, that is why it is this particular one is called the time complexity is expected time complexity of this particular one is order of log n. Okay, that is the basic theory behind this particular one. To explain this particular concurrent skip list, I'm using the slides of Morris Herlihy and Anil Shavit. Okay, suppose if you want to get some idea on that particular concurrent hashing and concurrent skip list, you can refer the textbook Art of Multiprocessor Programming written by Morris Herlihy and Anil Shavit. When we look at this particular simple slide, you can see that here you can see a list with a set of nodes 0, 2, 5, 7, 8, and 9. Okay, this is a simple linker list. Suppose if you want to if we want to search for 8, okay, in that context, in the context of linker list, what are we going to do? We are going to start at 0. 0 is not the required node. Then we go to 2. 2 is not the required node. Then we go to 5. 5 is the required node. 5 is not the required node. Then we go to 7. 7 is not the required node. Then we go to 8. 8 is the required node. Then we return that particular one. That is a simple successful search in the context of linked list implementation. When we look at the linked list, this skip list implementation, okay, here what can you see? Suppose initially we are at 0. When we are at 0, as this particular node has some number of links, right? When we look at the top layer, this top layer is connected with node 9. So with the help, when we make use of the top layer, we cannot go to the node 8. Okay, but we are interested in node 8. So we can with the help, there is no use of this top level. Next, when we look at the level next to that, with the help of this particular link, we can go to the node 7. That means 7 is very close to 8. That means here we are skipping some number of nodes here, right? Here we are skipping some number of nodes straight away with the help of that particular link. We are going to the node 7. From node 7, we are looking for node 8. With the help of this particular one, we cannot go to the node 9, node 8. With the help of this also, we cannot go to node 8. When we use this particular link, okay, we can go to node 8. That means with the help of, when we take this particular path from this one to 7, from 7 to this one, we can quickly reach to the node 8. Okay. So here search time is logarithmic search time. Here search time is logarithmic search time. When the search time is logarithmic search time, we can perform insert and delete operations in log n time. We can perform insert and delete operations also in log n time. Is it clear? Is it clear? Is there any problem while understanding this particular one?
It's clear, sir. So
Okay, right. Here at the same time, here, this particular skip list is called a probabilistic data structure. Why it is called probabilistic data structure? Here, what is the height of number of levels of node 0? Number of levels of node 0 is, we can say that it is 5. Here, number of levels of this node 9 is also 5. Number of levels in this particular node 2 is 1. Here, node 5 is 3. Number of levels of that particular. That means number of pointers to that particular node, or number of pointers leaves that particular node. That defines the level or height of that particular one. Okay. In that context, that particular level is selected by using some a random number generator. That is why whenever we use some random number generator to fix the level of that particular node, then we can call it that particular one as the probabilistic data structure. Then we are going to use some little bit probability. Okay, then it is called a probabilistic data structure. Suppose here,
This pattern will change from time to time.
yeah, based on actually, if you create a list of skip list, you will get one pattern. If I
Okay.
create someone, I can get some other pattern. But actually, it maintains beauty of this particular skip list is, okay, it maintains logarithmic search time. Here, search time is logarithmic time. That means if number of nodes is n, we can perform such operation in log n time. We can perform such operation in log n. That is the beauty of this particular skip list. Next one is, suppose which data structures provide log n search time. Suppose if you consider AVL tree, in AVL tree, such time is in AVL tree, such time is also log n. Why it is log n in AVL tree? Height of AVL tree is log n. Height of reason behind that is height of AVL tree is log n. But the problem with that particular AVL tree in concurrent context is, okay, height balancing. Okay, suppose if multiple threads performs the concurrent insertions or deletions, then shape of the tree is going to be changed. When the shape of the tree is going to be changed, we have to adjust that particular, we have to maintain the height balance at each non-leaf node. To maintain the height balance at each non-leaf node, we have to perform some number of rotations, right? That is a costly operations. Okay, to avoid that particular one, either we can consider these kind of probabilistic data structures, either this particular one skip list or trips. In the last class, I discussed about trips. In trips also, such time is order of log n. Okay, there we are maintaining the height with the help of priority. Their priority is randomly generated from uniform distribution. Is it clear? Is there any doubt on the basics of this particular skip list? I hope that it is clear, right?
Yes, sir.
Here, there is no global rebalancing. There is no need to call global rebalancing as we did it for. Next one, in the skip list, there is one simple property. Here, that property is each layer is sublist of lower levels. Each layer is sublist of lower levels. That's it. When we look at this particular top layer, okay, then this in the context this consists of two elements. Okay, that those elements are 0 and 9. When we look at the only top layer, we can see only two elements. Okay. After that, when we look at the next element, next one, we can see three elements. 0, 7, 9. We can see three elements. 0, 7, 9. Okay. When we look at the next layer, next one, we can see four elements. 0, 5, 7, 9. Okay. When we look at the next one, we can see five elements. 0, 5, 7, 8, 9. When we look at the lowest level, okay, that lowest level contains the entire list. Entire list. Actually, we can use the all other levels to reduce the search time. Once we have reduced the search time, we can perform different operations on that one, either search, insert, and delete operations. That is the property. Actually, this is the property of skip list. Whenever we create a skip list, it should satisfy these two properties. First one is each layer is sublist of lower levels. Second one is lowest level is the entire list. Is it clear? Is it clear?
Yes, sir.
Yeah. Now, how can we perform operations, basic operations on this particular skip list? Okay, right. To perform basic operations on this particular skip list, suppose if there is a thread, this one is a thread. Some thread wants to perform contains operation. Okay, then what it has to do? Actually, suppose it is going to use node top layer. When it is used top layer top layer of 0.9, then it identifies that 8 is that one is too far. Okay, that is not the intended one. Then it makes use of the next layer. Then next layer is it points to 7. Oh, then it is close to that particular destination, right? Required node. Okay. Then actually what is going to happen is once it reaches to node 7, then it makes use of top layer of node 7. Top layer of node 7 is 9. Then it simply neglect that particular one. Okay. Then next one is again it points to 7 and 9. Reason behind that is this is a probabilistic data structure. Those links are not in our hands. Okay. With some probability, we are going to set the level of that particular node. After that, we are going to establish those links. Okay. How do we establish those links? Whenever, most probably in the next few minutes, I would like to explain how those links are going to be established and all those things. Whenever it uses the next one, that is this one, then also it is little bit too far from 7. Then also it neglects that particular one. Then it makes use of next level below that. Next one is this one. Here, this particular one points to node 8. Then that is the required node for the given thread. When it finds the required node, yes, okay, that particular search returns true. That particular search returns true. Are you with me? That is simple search process. If a thread wants to perform a such operation, it makes use of that particular path. Right. Here, why I already discussed why it is logarithmic one. Next one here is this is simple math to get the logarithmic time. Each time it is going to roughly jumps 2 power I nodes. When it jumps roughly 2 power I nodes, we can reach to the given destination in log n time. Because reason behind that is at 2 power k. K is the number of skips. Okay, 2 power k equal to n, k equal to log n. Next one. Here, next one is suppose if you want to perform, yeah. Now, the next one is I would like to uh, insert. Okay, they actually unsuccessful search. It returns this one. Suppose if I want to insert some node, okay. Suppose if I want to insert 6, how that particular node is going to be inserted. To insert any node, first of all, we have to find where the node 6 is going to be inserted. Suppose if I want to insert 6, where 6 is going to be inserted, 6 is going to be inserted between 5 and 7. 5 and 7. Okay. So in that context, we have to find predecessors for the 6 and successors for the 6. Once we identify the predecessors and successors, then we are going to establish the links between those two. Okay. Right. Here, I need a little bit time to explain that particular one. Yeah. Here, let us see. A thread wants to insert 6. Where 6 is going to be inserted? Actually, based on that particular 6 is going to be inserted between 5 and 7. Okay. To insert a 6 between 5 and 7, what it's supposed to do? It's supposed to actually to insert 6, we have to find the height of that particular one. That height is generated with the help of some random number generator. Okay. Height of all these nodes are generated with the help of some random number generator. Then only we'll get the log at such time. Suppose a random number generator generates the height of this particular node is node as 4. When generates this particular height of this particular node as 4, in that context, what will happen? Okay. Now we have to identify predecessors and successors for this particular 6. That means we have to give 4 predecessors and 4 successors for this particular given node. We have to identify 4 predecessors and 4 successors for that particular one. Okay. What are the predecessors? Suppose if 6 is inserted between this one. What are these 4 predecessors links for this one? Here 6 is inserted between these two nodes. 4 predecessor, this is a predecessor link for 4. This is also predecessor link. This is also predecessor link. This is also predecessor link. This is a predecessor for 6. This is also predecessor for 6. This is also predecessor and so on, right? What are the successors for that? Successors for that one is, okay, 7. Only 7 is the successor, right? All these predecessors points to 7, right? Only 7 is the successor. Are you with me? Are you with me? Yeah. To identify that, yes, I would like to give little bit example for that. Yeah, this is the case. Suppose consider, actually, I want to perform the insert of 6. To perform insert of 6, actually, I'm going to calculate predecessors for 6. Okay. Here, assume that the level of that particular one is 4. Okay. That level is generated by using random number generator. First, that is the predecessor. That is the lowest level. Next one, this is also predecessor. This is also a predecessor. This is also a predecessor. Once we have all those predecessors, next one, we are going to identify successors. 7 is the successor. Similarly, with the help of that links also, we get 7. This is also 7. This is also 7. Now, we have predecessors and successors. Once we have predecessors and successors, yes, now we are going to insert 6 between these 5 and 6. Once we insert 6 between these 5 and 6, later we are going to map these predecessors and successors. Are you with me? Okay. Now, actually, see. Now we are going to insert here. This is the gap. Okay. Here we are going to insert 6. So 6 is going to be inserted 5 and 7. First of all, what we have to do, we have to find the predecessors of 6 when the level of 6 is 4. Okay, when the level of 6 is 4, we have to identify predecessors. Once we identify the predecessors, what we have to do in the concurrent context, we have to equate the log on predecessors. So on which set of nodes we have to acquire the lock? Here, these are the predecessors. We are going to acquire the lock on this particular node 5 and this particular node 0. Once we acquire the lock on these two, okay, we have to insert this one, 6. We are going to acquire the lock on those two nodes. Once we acquire the lock on those two nodes, okay, we are going to validate it. That means, yes, those nodes are reachable from the first node, head node. Once we validate it, later what we have to do is just like what we did it in an optimistic search. After that, yes, we have to insert 6 between 5 and 7. Once 6 is inserted, okay, we have to adjust appropriate predecessors. Okay, actually in just a few minutes back, I discussed about predecessors and successors. Predecessors and successors are also a kind of arrays, right? Okay, with the help of those pointers, we are going to adjust predecessors and successors of the 6. Okay, that is a simple mechanism to perform the insert operation. Do you have any doubt while understanding this particular one? This is a little bit tricky one. We need a little bit patience to understand that. Okay. Do you have any doubt? Again, I'm here to repeat it or to clarify your doubts. Here, job is very simple, right? Here, job is we have to add 6. Okay. To create a 6, to add 6. Okay. Here, height or level of a node is randomly generated by using some random number generator. Here, random number generator generates the height of the node or level of that node is 4. That means we have to take care of 4 predecessors and 4 successors to that particular node 6. Suppose if node 6 is inserted between 5 and 7, what are those 4 predecessors? These are the 4 predecessors. So if these are the 4 predecessors, we have to acquire the lock on these predecessors. So here we are going to acquire the lock on node 5 and node 0. There is no need to acquire the lock on node 2. Reason behind that is 2 is not a predecessor at all in this particular case. Is it clear? Is it clear?
Yes, sir.
Okay. So once we acquire the lock on all its predecessors, then what we have to do? We have to validate those predecessors from the head node. That means here actually 0 is the head node. Okay, some cases 0 and those predecessors need not be a head node. In that context, what we have to do, we have to validate whether those nodes are reachable from the first node or not, or a head node or not. Okay, if it is reachable from that head node, then it is fine. Then we can comfortably insert that particular one between 5 and 7. If validation is failed, means that some other thread performs the update operation on that particular skip list. So what this one has to do, this one has to release the logs and again perform the search operation. After performing such operation, it has to identify required number of predecessors and after that again acquire the log and do the insert operation. That is the logic. That is simple optimistic set. Here we are going to identify that. After that, we are going to acquire the lock on predecessors. Next, we are going to validate it. Once validation is done, validation is perfectly fine. Then we are going to insert that particular one between 5 and 7. Okay. That means actually then we are going to adjust all those predecessors and successors are 6. Okay. That is the case. Next. How can we perform remove operation? Suppose here we want to perform a remove operation. How can we perform it remove operation? Suppose in the context of lazy list implementation, how we did the remove operation? Initially, we did the logical removal. Later, we perform the physical removal. Here also assume that there is a bit to perform the logical removal. Okay. So to perform a remove operation, we are going to identify predecessors of that particular given node. Suppose if you want to remove 6, okay, we are going to identify the predecessors. These are the predecessors for 6. Next one, log the victim. This is the victim. So we are going to remove this particular one. After that, what are we going to do? We are going to perform logical removal. Okay, set that particular marked bit. That node is logically removed. Once the node is logically removed, what we have to do? We have to adjust all its predecessors. That means this node is logically removed. If this node is logically removed, this predecessor should point to the next node, this node. This one should point to the next node. This one should point to the next node. This one should point to the next node. We have to do all those adjust operations. To perform all those adjust operation, we need this find operation. In find operation, instead of finding only one predecessor, here we are going to find set of predecessors for that particular given node. Is it clear? Is it clear?
Yes, sir. Sir,
Yeah.
why this 2 is not considered as a predecessor?
No, no,
Because
no. So, what is the meaning of the word predecessor? Here, meaning of the word predecessor is, okay, we can reach to the node 6. Okay. Yeah.
okay, so connectivity is not there. Okay,
Connect from 2, there is no direct connection to the 6, right?
okay, sir. Okay,
Yeah. Suppose if you want to reach to go to this to 6,
okay,
we have to go to via 5.
okay. So which are all directly connected? 5 and 0. Okay.
Okay. Right. Next one. Here, actually, to avoid, actually, in concurrent context, we have to take care of deadlocks, right? So we have to avoid the deadlock situation, we have to acquire the locks in certain order. That is, we have to acquire the locks in ascending order. That means from left to right. Suppose we have some set of predecessors. In that particular context, suppose if you want to acquire the lock, we have to acquire the locks in the left to right order or in the ascending order. Is it clear? Suppose if one thread acquires the locks in this order, another thread acquires the lock in this right to left order, then there is a possibility of live lock. We have to avoid those live lock situations in the concurrent implementations. Is it clear? That's what I discussed in lazy synchronization or optimistic synchronization. Is it clear? Simple case. Simple. Here I would like to give a simple example. Suppose to perform this insert operation or remove operation, one has to acquire the lock on this one. One has to lock on this one. In the particular process, okay, one thread acquires the lock on this one, T1. Later it acquires the lock, T1. This acquires the lock at timestamp 7 hours, 45 minutes, 50 seconds. This acquires, same thread acquires the lock on 7 hours, 45 minutes at 51 second. 51 second. Another thread, T2. T2 is also going to perform, T2 is also going to insert some node between 5 and 6, that is 5.5. Assume that. In that context also, predecessor, that also assume that level of that node is also 4. Then we can have same set of predecessors. In that context, T2 acquires the lock at 7 hours, 45 minutes, and 50 seconds. But during that time, T1 did not acquire the lock on this particular one. After that, T2 is going to acquire the lock on this particular one. Here, when you look at this particular scenario, if we are working with only one thread, there is no problem. If you are working with multiple thread, here T2 acquires the locks in right to left order. T1 acquires the lock from left to right order. Okay, here at 50 seconds, and T1 is going to acquire the lock on 51st second, right? Here T2 is going to acquire the lock on 50th second. Actually, 51st second, actually it is going to acquire the lock on node 0. Then T1 can acquire the lock on only one node. T2 acquires the lock on only one node. So to perform that particular operation, both the threads need a lock. Both the threads should need a lock on both the nodes. Actually, if the threads follow different orders, then there is a problem. Here there is no problem is live lock. Okay. So to avoid that particular one, both the threads should follow the order left to right. If both the threads follow the order left to right, okay, both the threads trying to acquire the lock at the timestamp 7 hours, 45 minutes, and 50 seconds. If both the threads put a request at the same time, by the definition of lock, okay, it supports the mutual exclusion property. Then in that context, only one thread, one of those two threads will be allowed to acquire the lock on node 0. So second thread is going to wait there itself. Okay, it cannot proceed further. So thread which acquires the lock on node 0, that particular thread will be allowed to acquire the lock on node 5. Is it clear? Any doubt? Can I proceed further?
Yes, sir.
Okay. So when we look at this particular one, okay, log the predecessors in some particular order, either in ascending order or descending order. That depends upon you. Okay. Uh, After that, we are going to perform the delete operation. Okay. Then physically remove it. Then when we physically remove it, we have to adjust all its predecessors. Is it clear? Next one, contains operation and node is marked. Okay. When can you say that whether node is there in the particular skip list? Okay. To say that particular one, we first of all we have to reach to that particular node. If that particular node is reachable from the node 0, then there is a chance, right? After that, we are going to verify marked field. Okay, if marked field is green, then it is there in that list. Otherwise, if it is red, then it is not there in that list. Okay. Yes, here there is one more problem. Problem is node 6 is removed while being traversed, right? When do we get that particular possibility? This particular thread, okay, reaches to the node 8, okay, in such process. After reaching to the node 8, operating system may suspend this particular thread. Reason behind that is, okay, operating system usually there is limited number of resources. Operating system executes the thread in round robin fashion. Okay, that is not in our control. Okay, in that context, when this particular thread is in suspended state, some other thread may remove the node 6. When some other thread removes the node 6, what is going to be happen? That particular thread, whenever this particular thread is resumed, that is on the logically removed, that is on the removed node. Okay, here to give the correctness of contains operation, we have to give the some other guarantee. That guarantee is, okay, that node 8 is reachable from the removed node. Okay, node removed while being traversed, and if some other thread is there on that particular node, okay, after some time that particular thread is resumed. In that context, we have to give a guarantee that that particular thread is reachable to the node 8 from the removed node. Then only our algorithm is correct. That is why, okay, we can say that this is art of multi-programming. Okay, here we have to concentrate on different things. That is why it is art. It is actually, up to some extent, it is a science. Okay, after that, it is an art to write multi-thread codes. We have to give a guarantee that we have to prove that unmarked node 8 remains reachable from the remote node. Next, usually we use the concept of linearization in concurrent programming or multi-core environment, what is the term linearization means? If a thread performs a particular update operation, we can say that that particular update operation should be visible to all other threads. When that particular update operation is visible to all the threads, that particular point is called a linearization point or LP point. Here, in the context of remove operation, whenever we update this particular bit, okay, from green to red or pink, then we can say that that is the LP point of remove operation. LP point of remove operation. Is it clear? LP is very, very important to give the proof of correctness. In all concurrent implementations, to give the proof of correctness, we have to say that after so and so point, changes made by the one thread are visible to all other concurrent threads. Is it clear? That is linearization point. That's what, while discussing sequential consistency and quiescent consistency, I discussed about these LP points. Okay. Next one is, when do you say that linearization point of add method? For add method also, we are going to add these links, right? One by one, one by one, one by one. Okay. This one is add. This node is fully linked. For that also, we are going to maintain a single bit. Okay. After fully linked, we are going to update that particular one. Then we can say that that particular that is the linearization point of add method. Next one is linearization of contains is somewhat tricky. Why it is tricky? Suppose if you want to give the linearization of 7, okay, contains method actually is actually this particular thread wants to verify whether contains 7 is there in the given list or not. In that particular process, it reaches to the node 6. After that, some other thread deletes that particular node, and that particular thread is in which state? That particular thread is in sleep state. Okay, when that particular thread is in sleep state, some other thread, performs okay, some other thread performs actually insert of 7. Whenever some other thread performs insert of 7, okay, then what can you say that whether this particular thread say that it should return true or it should return false? What is the linearization of this particular thread? Okay, linearization point of that particular thread should return false. Okay, so if it returns false, then what is the linearization point of that particular one? Linearization point of that particular one is, here some other thread inserts 7. Linearization point of this particular thread, LP of this particular thread, is just before this particular node is going to be inserted. That is the linearization point. That is why linearization point of contains operation is somewhat tricky in lazy list implementation and this one skip list implementation. Okay, to get the more clarity, please open the prescribed textbook and go through it. You will get some clarity. If you don't get any clarity on that linearization point, most probably I will discuss in the next class. Don't worry about that particular one. that is next one is yeah, there is simple experiment. Actually, here when we compare sequential implement, the simple sequential implementation. This is simple sequential implementation of a single linked list, skip list. If we consider this one, what is one? Concurrent implementation of skip list. We can get the better throughput. We can get the better throughput. See that here throughput is this is in terms of when throughput when the number of threads is 60, throughput is always fixed in sequential implementation. As we increase the number of threads in concurrent implementation, we can get the better throughput. Okay, here you can clearly observe speed up is at least 12x speed up. Here speed up is 12x speed up when the number of threads is 60, right? The number of threads is 60. We can observe 12x speed up. Okay. Right. That is the little bit theory behind that. After that, okay, I would like to I would like to show the code. I would like to show the code. I think you are able to see the screen, right?
Yes, sir.
Okay. NSM. EI. Skip list. Yeah. This is the skip list code. Okay. Here, maximum level of this particular one is 32. Okay. Next one is actually to generate the random number, we have to supply the appropriate seed. Otherwise, if a seed is fixed, we always get the same set of numbers. Okay. That is one. After that, this is the logic to generate the random level. Okay. After that, in this way, actually, we are adding something into that particular skip list. To add something into skip list, we have to find the predecessors and successors. Once we find the predecessors and successors, we have to insert that particular given node into the skip list. Okay. Similarly, to perform the remove operation, then also we have to find the given predecessor and successors. Later, we have to perform the appropriate deletion operation. Yeah. Here, contains operation is somewhat easy for you. This is the contains operation. When you look at this particular contains operation, what can you see? Okay. Here we are going to identify, we are going to call find. Okay. We are going to verify whether X is there in the given list or given skip list or not. To find that X, we are going to call to find X comma predecessors and successor. In that process, we are looking for X. If X is there, we are going to find the predecessors and successors of X. Okay. Next one. Here, what are we going to do? We are going to verify, okay, fully linked bit, whether that particular one is fully linked or not. If it is fully linked, then only it is in the list. Otherwise, it is not in the list. Okay. Next, we are going to verify whether it is marked or not. If it is not marked, then only it is there in the list. If it is marked, then it is deleted, logically deleted from the list. Okay. If it is found, okay, then its value is, okay, that if it is found, then its value is something, right? Here, what is the logic? If L found value not equal to -1, okay, that means that, okay, if the particular one is there in that list, okay, then its value is -1. Okay, are you with me? I think I missed
Yes.
you. Okay, yeah, actually, this is simple condition to verify whether the given node is there in that list or not. Okay, right. A simple condition, if L found value, okay, equal to -1, means that node is not found in that list. Okay. Here, what is the condition? L found value not equal to -1. That means given value is there in the list. Okay. If it is there in the list, we are going to verify, okay, whether that particular node is fully linked or not. If that particular node is fully linked, then fully linked bit value is set. Okay. After that, we are going to verify, okay, if whether that particular node is marked or not. Okay. If it is not marked, then only we have to consider. Otherwise, there is no need to consider. This is simple contains operation. Okay. Here logic is, okay, for all the operations. To understand this particular piece of code, we have to understand this particular find of x comma predecessors comma successor. Okay, that is the important logic. If you understand that particular logic, you can easily understand insert and delete and such operations logic. Okay, that is the crucial thing. Where is that particular one? When you look at that particular one, this is the find logic. Okay, when you look at this particular one, for a given x, we are going to find predecessors and successors. Okay, initial value for a given x, here we are going to calculate hash code. That's fine. Okay, after that, we assume that initially L found value is -1. That is not there in the list. If it is there in the list, we are going to update that particular one. Okay, here we are starting the head node. After that, that particular one, always the sentinels have at the maximum level. Okay, we are going to use this particular simple logic to identify that particular one. Maximum level greater than 0. First, that means we start at level highest level, next lowest level, next lowest level, next lowest level, and so on. Okay, that is simple logic. Okay, after that, if you use that particular one, what can we do? We are going to verify, okay, uh, whether v value is greater than current dot key or not. If that should not be the case, okay, if that should if v value is greater than current dot key, then what we have to do? What we have to do? What is the meaning of that one? What is the meaning of the word current? Current is, okay, yes, predecessor dot next. Here we have a predecessor. This is the predecessor. Predecessor dot next is the current. This is simple linked list concept. Nothing great in that. This is the current. Okay. If this particular one, v is the hash code up for the given value. If v value is greater than current dot value, then straight away we can skip all these nodes between these two nodes. Straight away we can come to this particular node. We can use the pointers of that particular node. Okay, that is why if v value is greater than current dot node, predecessor equal to current, current equal to predecessor next. Are you with me? This is the logic. That means straight away we can skip all these nodes, right? Between these nodes. Okay. Yes, take some time, take your own time. When you take your own time, you can easily understand this particular logic. Nothing great here. Okay. Once we find, whenever we perform that particular one, we are going to update these predecessors and successors for a given node. Yeah, this is the logic to update predecessors and successors for a given node. Okay. Sorry. Yeah, I'm not interested in this particular. Here, I would like to execute this one. Let us see the performance. Here, when we consider this kind of skip list data structure, here I consider an object of type skip list, lazy skip list. Okay. Java C, list test.java. No problem. Now I'm going to execute this one, list test. One is the number of threads, 20,000, 10,000, 50%, 50, 75. Here, when the number of threads is 1, this is the throughput. When the number of threads is 2, what is the case? 1 point. We got the better throughput. When we increase the number of threads from 2 to 4, we got 1.9. Right. Actually, we perform the similar kind of operations on linked list also, right? See that list test. In list test, when we look at this particular one, lazy list implementation, this is a linked list implementation. This is also an ordered list. This is a lazy list implementation. For the same input, we are going to verify throughput for this particular one. Java list test, there is no problem. Yeah, when the number of threads is 4, let us see throughput. Here throughput is how much? Let us see the beauty of it. It is what is the when we use simple linked list. Here, what is the throughput? 0.05. When we use a simple skip list, that is also ordered list. This is also ordered list. Throughput is 1.99. How much speed up we can observe? We can observe 1.99, or simply we can say that it is 2 by 0.05. That is equal to 200 by 5.
40%.
No, 40x speed up. 40x speed up. 40 times speed up, right? Did you get my point?
Yes, sir.
Actually, no. If we get 2x speed up, then we can say it is 100% speed up. When we convert in terms of 100%, when we get 2x, it is 100%. Did you get my point? There is a difference between 2x and 40x. 40x means in terms of speed up, it is in thousands of speed up. 1000%, right? Did you get my point? 40x speed up.
Yes, 40x. Okay.
Okay. That is the beauty. That is why skip list actually, even though it is implementation is somewhat difficult, but actually for most practical applications, actually the speed up is comparable with trees. If you want to compare speed up of skip list with binary search tree, actually simple binary search tree, skip list is a better option. Okay. Suppose AVL tree also, suppose if you want to compare speed up of skip list with AVL tree, we can compare it. Now we are going to compare speed up of this one for trips. Almost this one is almost equal to trips. This is the trips we executed right yesterday, right? Java concurrent trip test 4, number of threads is 4, and this is 1000, 50, 50, 75. Here the trips is 4.4, right? Did you get my point?
Trips is even very
Better option.
better option. Okay.
That is why I got the publication. I think great in that.
Okay.
Okay. That's it. That is about a script list. Anyhow, I will share all these slides with you and programs with you. What we can
How to do the real world program this profiling, sir? So like this without tools.
No, actually, simple thing is Linux tools are there, right?
Sir.
Perf
Perf.
tool, Perf tool is
Ah,
there. That is one thing. Okay, with the help of Perf tool, you can find number of cache misses. Okay,
okay.
not only that, actually you can find number of page faults and all that information. You can get it with the help of Perf stat. With the help of Perf stat.
Okay. Okay.
Next one is when I use this. When you use, suppose if you want to know the size and memory footprint information, here you can use some other thing. Here you can see that, right? Total memory, free memory,
Okay.
user
Oh,
memory, total minus free, right?
yes, sir.
Yeah, if you remove that particular comment, you can execute it. You can get some information about the memory also.
Okay.
Okay. Here, actually, this is the actually you have to execute all these things. You have to remove all these comments.
Okay.
Okay, runtime and remove this runtime.gc garbage collector. Then here you are going to call the garbage collector. Next one is this one is runtime.available process and all those things. Okay. Yeah, actually, I provided a little bit test bed here, right? Actually, while I was doing PhD to build this particular program. Okay, initially I don't have any idea on this particular one, how to test the given code, piece of code, and all those things. Okay, in that during the time, I spoke with researchers at Technion and Brown University. I spoke with Maurice Herlihy. I got some inputs from them. They didn't share their code with me. I got some inputs from them. Based on their inputs, actually, I developed this particular wrapper class on my own.
Okay. Okay, sir.
Okay, na? That's it. Thank you. Do you have any other doubts?
Sir. Thank you, sir. Yeah. Yeah.
Yeah.
So basically, so we have to check uh, this throughput and other things for CPU things and memory footprints also. Then we have to modify the code and we have to again check.
Yeah.
Since it's
Yeah.
iterative process.
Yeah. No, no, yes. Actually, here one more point is that to verify the power consumption. Actually, when you look at my research paper, actually, I verified the power consumption also. To verify the power consumption, I used the PERF tool. No, no, no. I use RAPL tool,
Okay. Okay, sir.
running average power limit. Okay.
Okay. Okay.
Actually, to find this particular one Java programs, we can use JRAPL.
Okay. Okay, sir.
JRAPL is used to find the average power limit of Java programs.
Okay. Okay.
Right, that is the case. Thank you. Thanks a lot.
Thank you, sir.